probably the teacher that put those waste chemicals in there didn't really understand the hazards. Again, exposure that resulted in death. I just wanted to relate a few examples that didn't result in death at my own experience when I was in graduate school. The first one, I was in a lab, and it was an educational lab. We were doing a known experiment. Everybody in the lab was working with a little bit of sodium as part of the reaction. But at the end of the lab, one of the students came up to the instructor with a large lump of sodium in her bare hand and asked, "What do I do with this? Do I just throw it down the sink?" How many of you know what happens when you put sodium in water? It very quickly reacts, generates hydrogen and oxygen, and if it's open, it may just sputter and ignite. In an enclosed space like a drain, it could be explosive.
Deflagration, detonation, and destruction. Deflagration, detonation, and destruction.
Yeah. Fortunately, she asked the question, and that disaster was averted. But it could have been very serious. There was another one in a lab that I did not work in. A researcher was working with a high-temperature salt bath, not an uncommon activity, but it happened to explode. He was working in the lab at the time. He happened to be bending down, dealing with a vacuum pump underneath the hood that this bath was in. It blew up, blew the hood windows into the opposing wall, into the storeroom, where some of the storeroom workers were cut by flying glass. The walls of that laboratory space were bulged out. The door was jammed in place. Fortunately, there were no deaths. And the last one was a postdoctoral researcher in the lab that I worked in. He was working with a perchlorate salt of a metal compound that he was working with. He had probably less than a gram of material in a small flask, and he was collecting it. And he was working with it. He pulled his glasses aside to take a better look. It exploded, and he lost an eye, and he lost a couple fingers. What's interesting about this is that happened in 1984-ish. Years later, the same campus, same chemistry department, had a very similar incident involving peroxides. And it just points out the extreme hazard of working with peroxide chemicals. If you can substitute and avoid that, by all means do. Okay, so in the US, the OSHA laboratory standard basically sets a standard for laboratory safety plans and mandates certain components that be in that plan. And it applies to any laboratory that's small by definition, using any hazardous chemicals in a non-production situation. So there's separate rules and regulations that involve a production industry situation, mass production of any chemical or process. So it's very specific. This is a laboratory setting. It involves, working on small-scale experiments, things that you might be doing in here, non-production work, but it does apply in the US to a situation like you have here. And the central feature of the safety plan is the chemical hygiene plan, often referred to just quickly as CHP. We love acronyms in the US. I expect you probably do too, but when I say CHP, I'm talking about the chemical hygiene plan. So the employer, or the chemistry department, or the campus administration, they have to write this plan, and it has to meet certain specifications according to the OSHA laboratory standard. And the bottom line is that it must address virtually every aspect of procurement, storage, handling, and disposal of hazardous chemicals. And the point is to minimize, where you can, exposure to chemicals. And so you have standard operating procedures and best practices for handling those materials, requirements for control and personal protective equipment. And most commonly, we see this in laboratory fume hoods. Specifying waste disposal procedures. When I was at Berkeley, pretty much any waste disposal, they said, come to us, we'll take care of the disposal. They didn't want anything going down the sink in any appreciable quantities. It involves information and training, making sure that everybody in that lab is trained and understands the hazards and the practices, the behaviors that they need to perform in the lab. The last two, this requirement for prior approval, is kind of a narrow subset for extremely hazardous materials, carcinogens, toxics that are beyond the normal routine. And there's also establishing a procedure to avail medical treatment, at least diagnosis of anybody exposed. And that's specific to the US. I didn't see anything similar to that in India. So on the next slide, it talks about the chemical hygiene officer. And there could be a chemical hygiene officer for the whole campus, or there could be a chemical hygiene officer for the department, or in a research lab, it would be the primary laboratory supervisor. So we've said it before, and I'm going to say it again. Ultimately, the responsibility is the management. And so someday when you guys are management, it's going to be your responsibility to make sure that you're developing a safety plan. But also, as Catherine pointed out, we each are responsible for our own safety. So it's important that you be informed, aware, and most importantly, if you don't know, if you have a question, ask and find out. Don't just throw that lump of sodium down the sink. So, do we know if this is going to come back on? Now, when I was looking through the internet for anything comparable to the US chemical hygiene plan or the OSHA lab standard, I didn't find anything, but I did find some information from the Indian Institute of Science in Bangalore, and I found a safety manual. What I was hoping I would find for this campus. And in that manual, it has basic safety principles. It defines the Office of Laboratory Safety and Environmental Health and the safety network for the whole campus. And it outlines general safety practices, good housekeeping practices, personal care, personal protective equipment, glassware safety. It goes into details about chemical and biological safety. It highlights specific chemicals that are in the lab commonly but need extra care, such as hydrogen fluoride, volatile solvents that can burn, chlorinated solvents, peroxides, inhalation hazards. Talks about chemical fume hood usage, transport, storage, usage, waste segregation and disposal. So pretty much all of those elements that are in the lab standard in the US, they're incorporated here. And it's a very readable document, makes a lot of sense, provides a lot of good information. Now, one of the things, so we mentioned audits. If you go to their website, you'll find a self-audit form. And it includes these steps kind of as the introduction to the audit and outlines steps that should, basically how to perform the audit. So making sure that any mandatory signage is in the laboratory, and if not, it tells them where they can get it. Specifically says, look for personal protective equipment. Students should always have personal protective equipment, eyewear, lab coats. And if they don't, make a note of that, but it's a very important point to be looking out for. The lab in charge, or the supervisor, is responsible for laboratory safety. And so the users should be asked, what do you do? Who's in charge? Where do you go for information? They specifically tell them to look for improper chemical storage. Talk about that a little bit later, but you want to make sure that incompatible chemicals are not being stored together. Talks about labeling. Very important. Unknowns on the benchtop. You may know what it is now, but if you have to leave and come back tomorrow, it's like, well, I'm not sure what that was anymore. Talks about gas cylinders. It makes a point that exit doors in the laboratory must never be locked during working hours. You never want to trap somebody in a facility in the event of an accident occurs. They need ready, easy exits. And this is just the top of the audit itself. And so it's a safety checklist, goes down, says, is there a working telephone in the lab? Are emergency contacts listed near the telephone? Is the hazard sheet filled out and is it current? And are users wearing closed-toed shoes? It says some labs ask users to take off shoes. In such cases, replacement shoes should be provided, etc. So this is actually a 7-page document. It's not terribly onerous, but it's very useful for you to go through the lab and say, is my laboratory in compliance? And during the break, I was asked by one of the instructors and her students whether we had any projects for them. And this came to mind. If this is not in practice, you can go, it's really easy to find. You go Laboratory Safety Manual, Indian Institute of Science, Bangalore, and you'll see a bunch of links, and you'll be able to find this document. You could do this in your lab as an exercise and evaluate your own safety posture. The lab standard talks about standard operating procedures and standard practices. And I'm not going to go into a lot of detail there, but in these slides, it just talks about some of the basic things that we kind of all should know. No eating or drinking in the lab. Don't store food with chemicals. Keep separate refrigerators. Mouth pipetting. I came up in an era where the transition from mouth pipetting to using a bulb pipetter, people were still mouth pipetting in my younger years. But even 30, 40 years back, we don't do that anymore. It's just too easy to aspirate that chemical you're working with. There's no reason for it. very important. It's common in an educational research setting for individuals to have an experiment that may be running overnight. It may require somebody to come in and monitor. And they should never be doing any hazardous procedures, but they should always have access to safety in the event that they're in the laboratory alone. This is kind of a transition slide, but I was just looking at it as I was preparing. So I was talking about controlling chemical exposure. And so the things that should come to mind here are those institutional controls, such as fume hoods, and physical barriers, and PPE. And unfortunately, the illustration on the left shows somebody who's lost an eye because she's not wearing her eyeglasses. The one on the left does have eyeglasses. You've seen this slide before. The importance of eliminating the hazard, making a substitution. If you don't need peroxide, don't use peroxide. Creating engineering and administrative controls to separate the workers from the lab hazards. And finally, the personal protective equipment. While we say it's the least effective, we still all use eye protection, lab coats, gloves in the lab, because there's always that possibility of encounter. Fume hoods are probably, you're all familiar with them, and common in every chemistry lab. You can see on the lower left, that fume hood is just, there's something going on in there, some noxious gas cloud being generated. Unfortunately, the window is down low, that gas is being contained and exhausted. The center one is a good illustration of how somebody works in a fume hood. You can see that the sash it may not be at the appropriate level, but it's not wide open. You never want to work in a fume hood or leave the sash wide open. It's available to go up so you can move equipment in that might be too tall to get through the crack, but it should always be down with a minimum opening. And there's just an illustration on the right-hand side there showing a sticker that would commonly be seen on a fume hood saying, this is where that window goes. During operation, during work, you don't want it up, you want it down there. As far as using fume hoods, while it may be enticing to put your hazardous chemicals, store them in there, they're really not intended for that purpose. You don't want to fill your fume hood up with all your reagent chemical bottles that may be incompatible. It's a workspace, it's intended to be relatively open so that airflow goes through well. The other thing about this is that sash is all the way up, it's open. That hood is no longer collecting airflow. Any vapors there, a lot of them are leaking out. And this is a real problem in laboratories, in the design of the laboratory. There's a lot of air going up these fume hoods. They're sucking air out of the building. And the building has to be designed to have air freely coming in so that the air that's being drawn out is replaced. And it's a difficult challenge for your HVAC people, heating and ventilation people, to make sure that the fume hoods are operating adequately and the air is coming in. I don't think we're going to spend a lot of time with personal protective equipment. It's already been talked about in other presentations. But there's just some basics on the list. Appropriate clothing, gloves, and the right kind of gloves, eye protection, goggles, and possibly in addition to protective eye glasses, and face shields if it comes up. The face shield is a good one. When I was in graduate school, one of the things I was working on was a synthesis that required introduction of ammonia gas into the reaction. And we had an ammonia gas cylinder on the roof of the building, good place to keep it, a noxious gas that's very irritating. It's up there in an open space. And I was like, I don't want to go up to the roof and do my chemistry. So I created a little ammonia generator. I just had a solution of ammonia, and I plunked in a little sodium hydroxide. And in a basic solution, ammonia is expressed from that ammonia solution. You make it basic, ammonia gas comes off. And it worked great. Put in a little bit, I was getting little bubbles coming out, my reaction's going. I said, well, a little's good, more is better. Put a little bit more, and the whole thing just overpressured and splattered all over the fume hood. Fortunately, I was working in a hood with vertical sashes, so you would slide the windows left or right to work in. And I had the sashes in front of me, and I was working around, and so when it splattered, I was protected. So the chemical hygiene plan will also talk about the storage and disposal of chemicals. And it'll just talk about, the basic principles of how to store the chemicals and where to store them, any special requirements that are needed. So if it needs to be refrigerated, what kind of refrigerator can you use? The standard refrigerator can spark when that light comes on and ignite any volatile gases. This is also from the Indian Institute of Science in Bangalore's safety manual. And it's just a quick reference guide of chemical compatibility. So when you're putting your chemicals into storage, you can look at this and say, well, okay, I got something that's flammable. What can I store with it? You don't want to just store things alphabetically. Acetone with acids, and you want to avoid those chemical incompatibilities that can result in a violent chemical reaction if something were to spill and interact. This is talking about the labeling. So on the pictures that we're showing here, one is a dish of wax, and the other is, I think, sodium hydroxide in this example. They look the same. You can't really tell just by appearance what's what. And this is a relatively innocuous example. I mean, the sodium hydroxide is a hazard. It's not an extreme hazard in this form. And I'll just remind you of the GHS labels and the fact that the different components of the label, what's in the bottle, a signal word that identifies the hazard, a statement that goes into a little detail about that particular hazard, precautionary statement, first aid, and additional information. Very useful for working with the chemicals in your laboratory to look at that label and say, okay, these are the things I need to be worried about. Very important part of the chemical hygiene plan is training. So before working in the lab, all the workers, the researchers, the students should be aware of the chemical hygiene plan. There should be records kept of who's gone through training, what the training was. The plan should be reviewed and updated on a regular basis. We update ours in our lab annually. I think in the lab standard it has at least annually. And we are all required to review it annually. Even myself, I work in front of a computer all day. I'm not exposed to the chemical hazards in our lab on a routine basis. But I work in the lab, so I have to be aware. I will occasionally go in and talk to an instrument operator, analyst, and I'm in the lab space, so I need to be aware of the hazards that are there. So some more mandatory training requirements are outlined. One thing, the second line, a release of the hazardous chemical is going to be detected. And so this is just an element that gives you awareness of what to be on guard for. Are you going to see evidence of an exposure? So prior approval, again, this is for a special class, but the bottom line is if you don't know, ask. And this is important. I think a lot of us as students or graduate students, we may have an expectation that, well, we're supposed to know this. And I don't want to reveal the fact that I don't know this. For your safety and the safety of everybody around you, if you don't know, ask. Make sure you have that information. And again, this is specific to the US. I won't go there. These are kind of some illustrations of specific types of fume hoods that might be employed where you've got an extremely hazardous chemical or biological agent that you're working with. You need that to be contained. And that's pretty much it. So this last slide just kind of repeats the first slide, all the elements that were there. So, thank you. Where's Rampur? Any questions? Who wants applause? Can we get a microphone?
Hello, my question is, sir, what if there is a power outage or like failure, equipment failure during an experiment involving heat or pressure? So what should a person do in that case? And what should be the measures he should take?
I'm sorry, I couldn't understand.
I'll repeat, sir, I'll repeat. What if there is a power outage or equipment failure during an experiment involving heat or pressure? So what should a person do in that case? Like what should you take the measures?
So you had a power event.
Yeah, power outage. Power outage or equipment failure.
Well, in any case, if something's out of control, you get out of the lab.
Yes, sir.
You notify somebody
If
get to safety first,
yes, sir.
and then deal with the problem.
Like if the person cannot get out of the room, what should be the first measure he should take? In case, like if he can't get out of the room, so what should the measure he take?
If you can repeat it, Rampur, did you hear it?
Brandon,
Yes.
the question is, someone in the laboratory could not get out. What are the approaches to help them get out? Are there any?
Well, every situation is different. It could be that the hazard is lighter than air and is up here. And if they can crawl to the door, staying low, that may be the safe route out. It could be heavier than air, in which case that's not true. They shouldn't be in that space alone, first thing. There should be phone in the lab, second thing, if they can get to that and they can't get out. But you don't want to have that situation. You don't want to have a locked lab that you can't exit. But if you are able to isolate the problem. So for example, something's, power's lost for the fume hood, it's not working. You can still close it and minimize the leakage from the fume hood into the lab space.
Did you get the answer? Good, come on over. You see, more and more people are awake. Do you know that? There were 3 hands up for questions, comments, and that's an improvement. Brandon, what do you think? Is that an improvement?
Yeah,
Okay.
I'm glad to see the number of people that are back after lunch.
Yes, yes. So wonderful. This is a small token for you for being bold and being awake and stood up. Thank you. Okay, do we have any other mementos? Richard, do we have any mementos left? Okay, then I can ask. Oh, you have one more? Okay. Okay, firstly, you have a question or you are going to answer a question? You have a question. Okay. What is the question?
Sir, it's Pratik here. Sir, do laboratories conduct regular audits?
I'm sorry, repeat that?
Sir, do laboratory conducts regular audits?
Do laboratories have to have audits?
Yes.
Well, at the Indian Institute of Science, they do. So they have both audits at the institutional level, but they also have their recommended self-audit, which anybody can do at any time as a student or as the lab supervisor. It's a good practice it helps you become aware. It points out in a systematic way things that you should be considering. So, yes, do an audit.
Thank you. Are you satisfied with the answer? Wonderful. So here is a memento for you for being bold, being awake, and asking a question. Do we have any other? Okay. Oh, look at that. Let me finish this gentleman and then I'll come there. Okay.
Sir, myself Shashank. Is there any procedure to conduct self-audit? Can I know it?
Any procedures
For self-audit?
cell phone?
Yeah, audit.
Cell phones are great. I mean, yeah. Oh, yeah. Oh, I mean, that was on the slide. And you can, if you just do a Google search, Indian Institute of Science, Bangalore, safety manual, you'll find links there from their Department of Health and Safety, and you'll find that lab audit document. You can download it, perform it.
You have shown the PPT on, according to that Indian, this slide, right? Is there any universal procedures according to self-audit?
I didn't find anything in terms of Indian regulations governing laboratory procedures. My guess is the Indian Institute looked at the American model and said, this is a good practice, this is what we're going to follow.
Thank you.
Thank you, Brandon.
That's not necessarily definitive, but I didn't find it.
Oh, ನಿಮಗೆ ಒಂದು ಮೊಮೆಂಟೋ ಕೊಡ್ಬೇಕಲ್ಲ ರಿಚರ್ಡ್ do you have one? Please bring it up. Oh, okay. So here, Kendra, have a picture with this gentleman. There was one. Okay.
Good afternoon, sir. Myself, Manashji. Sir, how does CHP guide the safe transportation hazardous chemicals within the laboratory?
Francois, are you able to repeat that question?
How does CHP guide us to transport hazardous chemicals within the laboratory?
It doesn't really cover within the laboratory.
Yes, sir.
Yeah, so it should have things like using carts, using a secondary containment bucket for large bottles of acid or base. I mean, there's a lot of standard things that should be specified or illustrated within the manual.
Okay, are you happy? Wonderful. Richard, Kendra, do you have any mementos?
I can relate another incident in my laboratory
Okay.
where my lab mate was working with a gallon bottle of sulfuric acid.
Stand for a picture.
And this was before the sulfuric acid bottles were rubberized. He accidentally bumped it and broke it, so it spilled out in the lab. He happened to be right next to the lab shower, but he didn't think upon the shower. I was working at my desk, and I just reached back, pulled the shower, and kept him under it. But it was immediately burning through his shoes. I mean, in seconds, the sulfuric acid was burning through his shoes, and he was feeling it.
Thank you, Brandon.
It happens in an instant.
Thank you very much. ನೀವು ಫ್ಯಾಕಲ್ಟಿ ಅಲ್ಲ ತಾನೆ?
Excuse me, sir. Sir? Sir, there is one question about if anything happens, like if a fire accident has happened in the chemistry department or in the chemistry lab, we can't use any fire extinguisher there because of the hazard chemicals are there. So in that situation, how we need to handle or how we need to deal with that situation? We can't use any fire extinguishers because some other chemicals may affect due to that.
When I was at Berkeley, our training then was get out of the lab. Unless it's a small fire and you know what it is, you know that, I mean, you should have a general purpose fire extinguisher in the lab that can handle most common chemicals, most small fires. But basically they said, you know, if it's more than small, you get out and let the fire department to deal with it. They come in with their big hoses of water, basically. And I think that's generally the response. I mean, if they know that there's, you know, reactive metals in there and that's really the principal cause, they'll come in differently. But their general response was lots and lots of water. But your response is, unless it's really small and you can deal with it and deal with it immediately, you leave and close the door and make sure other people know what's going on. Call the fire department.
Thank you, Brandon.
Thank you.
So I would like to present a memento to this individual for again participating in the questions and looking for some answers. Thank you very much. Okay, next presentation, please.
Thank you, sir. The next session speaker is Miss Adrian. Miss Adrian receives a PS in Chemistry from the University of California and MS in Environmental Management from University of San Francisco. In 2010, she was stationed in Bangalore and received a Fulbright Nehru Scholarship in Environmental Leadership. She is a recognized editor in the field of hazardous material management. She is currently editing the 4th edition of the IHMM text Managing Hazardous Material. Welcome you, ma'am.
afternoon. I'm going to talk about something a little different than what you've been hearing for the past day and a half. I'm going to talk about what happens when the chemicals that you use are in the environment and how do we address those as a society and as a regulator. So I'm a regulator, and a small part of what we do is enforcement. Most of what we do is develop partnerships and provide money and put projects on the ground to create clean water. So I'm going to start with 4 things: a line, a circle, connection, and wisdom. I remember when I was your age. I know that's hard to believe, but I do. And I remember my life then was a line. I had gone to school, grade school, high school. I went to the university, and when I got out, I was going to have a career. And my career was going to lead to success. And success was a straight line. Little did I know when I actually did graduate and start my career, success was not a straight line. And as I get older, and now that I'm near the end of my career, success looks like a circle. And the circle is having a connection, and that connection is you. I'm so honored to be here to talk to you, because you're going to start your circle soon. And while I will provide you with some wisdom, I'm going to ask you to provide me with some wisdom as well. So here's water. Wow. Aside from being like a really cool chemical, water is essential to life on Earth. And it is so essential that every single religion, every single spiritual culture has ascribed a meaning to water of purity, life, fertility. Perhaps you can recognize this place. So some big facts, really big facts here. And I think what's really interesting about these big facts is 71% of the Earth is covered with water, and 70% of our bodies are made of water. But what is also really interesting is to look at the amount of usable water on our planet. And of that, only 0.031% is easy to get. At the bottom, there's a little factoid for India. The average consumption of water is 3,800 liters per day, with 8.1 billion people. 30,780 billion liters of water are consumed in India every single day. So here's a little diagram of the Earth, and the big blue circle shows the amount of liquid fresh water, and the little dot, little tiny dot, is the amount that's actually easy for us to find and use. And water acts like a transportation system, right? And not only does it get transported around the globe, it transports chemicals around the globe. So some of you may already be familiar with polychlorinated biphenyls or polyfluorinated alkyl substances. You'll hear more about those later on, but let's just say they cause health problems. So let me ask you a question. How many here like Pizza Hut? Okay, got 2 Pizza Hut people. I bet there's more. Oh, a third one went up. Okay, so when you get that Pizza Hut, what does it come in? A box, right? Possibly a coated box. Possibly a box coated with PFAS. What if you throw that box on the ground? Does that matter? How much does that matter? Does it matter to you? Does it matter to someone else? Well, the fact is, if that box has PFAS in it, and it rains, the PFAS will enter into our water system. And our global transport will carry that PFAS up into the stratospheric winds to the Arctic. And there are people who live in the Arctic who don't eat Pizza Hut, who have never seen a Pizza Hut box, but they experience exposures to PFAS in their foods. And surprisingly, those exposures come more from the natural environment around them than from when they go to the store and buy things that maybe were produced down here. So what's the lesson learned? You know, that lesson learned is that what we do makes a difference. And we use chemicals here that impact other people who have no benefit from those chemicals. So we talk about circles, and that is what the hydrologic cycle is, right? Water is all about circles. The sun warms it, takes it up into the atmosphere. Where we live, we have mountains, and it comes down as snow in the winter, just like the Himalayas. And we have to have that snow. If that snow is a reservoir for us, if we don't have enough snow, we have drought in the summer. And in India, you have a similar situation with monsoons. They drive agriculture. If you don't have monsoons, you have drought and you have crop failures. So this water cycle is not just water quality, but also water quantity. We had a question about climate change. What do you think the relationship with this cycle, what do you think the relationship is between climate change and this cycle? Any thoughts? Any wisdom here? Anyone want to take a guess? What's the relationship here? Stand up and say it. Yeah, and actually, you are really close to what I would say is the correct answer. The cycle is going very fast, right? And what's happening is as temperature warms, this cycle becomes more unpredictable. It's not that the Earth is hot. The Earth has been hot before. What's happening is the change is moving faster and faster. And when we have economic systems that rely on being able to predict snowpack or predict how much water we have to grow our crops or predict when they will grow, when that is disrupted by climate change, it affects our society and our economies. All right, so there's water and then there's water. Like, I really like to buy Indian clothing. Thank you for letting me wear it. I appreciate that because I love it. When I take this dress home, am I taking water home with me? Think about it. How am I taking water home with me? It takes water to manufacture this dress. So when I take this water home, when I take this dress home, I'm taking a little bit away from you. Thank you. Thank you for giving me your water. I love your clothing. But it's something that we need to think about when we buy products and we have a social responsibility towards others, especially towards areas that don't have enough water, right? Another point of fact is that the garment industry not only impacts water quantity, but it impacts water quality. It is one of the highest polluting industries, possibly in India, because of the way water is managed in that industry. So given all the things I've told you so far, please share your wisdom with me. Why do we treat our waters and our people like this? I want to know. I want to hear your wisdom. These are not pictures from India, although they could be. These are pictures from around the world. So we do this in many places in the world. Why? I will say that while this is very hard for me to look at, and it should be hard for you to look at too, we do have tools to get to clean water. And that is what our regulatory framework is about. We have the Clean Water Act in the United States, and it is very similar to what you have in India under the Environment Protection Act. Anybody here studying the ISO systems, 9,000, 12,000? Anyone familiar with those? Okay, so when you start your straight line rocket out of the university, what you will encounter in many factories and businesses is something called ISO 9000. And if you're doing environmental work, ISO 12,000. Both of those are management systems, and they create what is called a plan, do, check, act way of thinking about things. So for the Clean Water Act, that plan is to set a goal, and that's what our water quality standards do. They give us the criteria that we need to check our waters and see whether or not they're clean. So we set the standards, and then we assess the waters. We go out and do tests, and we collect samples. We identify whether or not those meet those standards. When they don't meet standards, then we create a cleanup plan. We also call the water quality budget, and we use that plan then to create a way to get to clean water. So the water doesn't meet standards, but we want clean water. And then we implement that plan, and typically we do that through permits, through technology, and through actions leading to behavior change. Every 10 years, we check on progress. Anybody recognize this? You should, right? This is where you live. So, we have a concept that we use all the time called watershed. A watershed is a physical thing. It's where the water drains from top to bottom, and everything in that watershed will enter into a specific water body, in this case, the Kaveri River, and it flows from west to east. A watershed is a physical, geographic thing, but I'm going to tell you it's also a people thing. And how do I know that from looking at this map? I'm assuming that these are administrative governmental boundaries of some sort, perhaps. I'm assuming that. I can see you have Tamil Nadu here, and I can see you have Karnataka. And look at the outline. The outline of the governmental administrative border for Karnataka is the Kaveri watershed, for the most part. And why would I care about that as a regulator? Because I know in that area, people are going to care about their watershed, they're going to care about their water, and they will have governmental structures there to protect it. So once people become aware of what is happening in their watershed and they find they really care and they have the passion, right? And they find a way to organize and provide input. And once the governmental decision makers find a way to connect and to accommodate their input, then improvements can be made in water quality. And this is the principle that we use in our state to get to clean water, because frankly, most of our water bodies do not meet water quality standards. I'm going to share a concept here, and this is important that you listen, because I'm going to ask you again for an answer, and hopefully there's a brave person out here who will do it. And this is a clue. This is a clue to that answer. So this is the river that I live near, called the Spokane River. It starts over on the right side, goes across to the left side, and you can see on this map areas that are yellow and areas that are blue. All right? So the yellow area is what we call a losing reach. So this is where the river flows and water goes down into the aquifer underneath. And so as the river goes downstream, it actually loses volume. What's interesting about this particular river is it has other areas that are called gaining regions. And it's where the aquifer is coming back into the river, especially this area on the left, which is very blue. And in fact, by the time the river gets down there, most of the aquifer flow is flowing into the river. This idea of gaining and losing reach could be used to solve a problem. So, stay tuned. All right. I live right about here, somewhere. This is a place down in the Washington State, way about as far away from me as you could get, in the area that I work. And it's called the Walla Walla Watershed. So you remember I talked about snow depositing on the mountains. The snow here deposits in that orange area. So in the wintertime, the reservoir snow builds up. But in the summer, as it melts, people start to grow crops and the water goes away. In this area, there is not enough water. There's just not enough water for all the people and all the uses. So what is a watershed to do, right? What do? They want to get along. They don't want to fight about the water. So they agreed. They agreed to do a 30-year plan to identify ways to put more water into the river. They wanted to consider the people, the agriculture, protecting fish in the streams, and controlling flooding. Those are the key things that they needed to look at when they wrote this plan. And they wanted to make sure that they included water quality in this plan because they are linked, as well as water supply for irrigation, floodplains, habitat for fish and animals, and following what they're doing to make sure that what they're doing is working. Okay, here is the problem, because this is what I do. I'm going to ask you to help me do my job. Okay? And I'm going to see if you can come up with some creative answers. So in this watershed, we have a wastewater treatment plant, a sewage treatment plant, and of course, it puts nitrates into the water. Remember the water quality cleanup plan I talked about? We have one of those too. And it says, during the summer, you need to remove your effluent from this stream because there's too many nitrates in it and there's no technology that you can use that will help us achieve our water quality goal. We also have this fish in the stream. This fish, called a salmon, is iconic to our area. There used to be millions and millions of salmon that would flow through these areas, and they're going extinct now. They need cold water, and they need water, period, right? I mean, if the stream is dry, they're going to be fish regardless, and if there's water there, it needs to be cold, and it needs to be without nitrates. So we now have a conflict because on the one hand, we need minimum flows for fish, especially during the summer, and on the other hand, we have to take the wastewater stream out of the river, which will lower the flows. Okay, it's your turn. Are there engineers here? Like civil engineers? No one to cop to that? Okay, there we go. You're on. Okay, so what would you do about this wastewater treatment plant? It has to meet water quality standards. Our water treatment plant says you have to remove it and you have to keep the flow of the river. What's your idea?
Wait. Go slow. Ma'am, when you try to build this wastewater treatment plant at that river basin where the aqueduct, like the infiltration happens in that aqueduct, so that whatever the impure water, it is seeping into the ground, and because of the natural purification which is happening through soil, and let it contribute to the underground water table, and somewhere at one place this water will come back to the base flow, which is adding up to the proper runoff of the stream. In that place, we will take care of, we will put the salmon, which is native to your region, we'll put this fishes over there, which means we can manage the water quality, we can take care of the fishes as well, and we can keep the stream running.
Excellent. Did you see my slides earlier? I didn't show them to you, did I? No. Okay. Excellent. Thank you. So I'm going to share the three options that we currently have.
Robin.
So the first option is remove the discharge, treat it on the land, which for us means growing crops with that discharge during the summer, and then store it in a lagoon when we can't grow crops, when land treatment is impossible. So this is a legal solution for us, but what is the problem? It takes the water out of the river, so it doesn't really solve the problem.
Adrian?
Yes?
If you forgive me, we'll just give a memento for asking that question.
Okay.
So, good luck.
Okay, here's the second option. We could remove the discharge and reclaim the water for irrigation. We might have to use a different water quality standard for that because it's a different use, but we could do that. That way, the irrigator is not taking water out of the river and that leaves the water in the river. So, another option. The third one is pretty much what was suggested. Congratulations. So this one is to move the water to a place where there is subsurface connectivity You treat the nitrates in that land column and you return the water via subsurface. Here's an example of exactly this concept in Oregon, a state that's south of ours. They put in the wastewater treatment plant, put in 120 acres of wetlands. Now they have water and birds come there. They have hiking trails. They have people who can recreate there. They restored some of the habitat alongside the river to improve conditions for fish. And they found out it was cheaper than what they had been doing traditionally for water treatment. So, my parting thoughts. Thank you for your wisdom today. Appreciate it. We all live on a land that's bounded by oceans, this big ball of water in the solar system, right? We all live on this big ball of water, and we are all linked with these living things, these fish, these things that live on the earth. We're all linked together by people, and as humans, we are all part of a community. So when I started with a line, a circle, a connection, and wisdom, I'd just like to say thank you very much for this opportunity to connect the circle and talk to you about water.
Thank you, Adrian, for providing water to drink.
For what?
Water
Water to drink?
for drinking.
Yes.
Thank you very much.
You're welcome.
Okay. I looked at a row where I said I will ask a question. Which one? Where is that row? Okay. I promise that I will come back, right? No? But I wanted to come back. Okay, one of you. 1, 2, 3, 4, 5. What did we talk about today? What did Adrian Borges talk about today? Who can raise the hands? Oh my God, they're all on strike. None of them want to get up. Oh, I can't. You can't even say one word. Please get up. Please get up. I will feel bad. I will feel bad if you don't get up. You don't have to ask her. Please get up.
We talked about water resource management.
Saragitta America.
Okay, the entire topic is about water. How can we save water? How can we manage?
Your friend could.
We talked about how can we manage the wastewater that is produced by us. Even like if there is a wastewater that we use on a daily basis is less than the wastewater produced by inactive activities like vehicles and other things.
Whatever you said, I will take it because you said water. Okay, that is acceptable. All the other things maybe or may not be, but at least you said she talked about water, right? So, Adrian, do you have any comment? Do you have any comment on what she said?
I think she got the point I was trying to make.
Good, good. So, do we have any mementos left? Richard? One second. Okay, Richard. Please, okay. we have a special PO, two people together. Finally, they said water. So they get a recognition of presenting a memento. And so that's good. Not a parade of matters. Okay. Next, do we have the next speaker?
Excuse me, yeah.
Hold on, one more question.
There's one small question here. There's a small question. One of our students wants to know, when you are leaving the treated wastewater to a water body, is the standard is 10-10 standards or 20-20 standards?
Oh, we would like the student to talk, Professor. Who is the student?
He's a bit shy.
Yeah, I would like that student to talk. Who is that? Okay. Please. Please.
Following 110 standards at 10 standards, no? It's a video TSS.
Don't get the feed from someone else. It should be your question.
Is
Anybody has any more mementos left?
Is the question about water standards?
Yeah, I'm going to make him ask the question.
Okay.
Please go ahead and ask the question. Professor, get ready. Oh, mother. No, he will come. Help. Don't feel shy. Go ahead. Pick up the phone.
So,
Okay, we'll skip that. Here is another question for you.
okay.
Myself, Rahul. I have a question like if those pollutants which have the same viscosity as water, how do we treat them?
I think I only understood half of that question.
Like if the pollutants have the same viscosity as water, how do we treat them?
If what is the same as water, how? So the pollutants have the same viscosity as water, how would we treat them? Okay. So every pollutant has its own chemical characteristics, and there are different processes we use to treat them. And organic chemicals, typically, when you think about viscosity, you're thinking about that. Usually in a water treatment system, there can be several different processes. Some could be separation, some could be filtration, and it all depends on the concentration of that pollutant in the water. So the facilities that I deal with are often municipal, city sewage, and the chemicals that we're treating are very low concentration, and so we can use membrane filters to remove those pollutants, for example.
Thank you, Adrian. Anybody has any mementos left? Richard, do you have a memento? Okay. Kendra, Robin, any mementos? Okay. Well, we don't have any mementos left, but thank you for asking the question. Thank you. Okay, thank you, Adrian.
Do you want to ask a question?
No, no, no.
Or teach you?
Yeah, question teacher.
Oh, over. This is over. Next time.
One officer, seven
Interesting point. On the head of the Chobita, wanted
and the
to
chairs are.
just a copy. But
Oh,
he
okay.
came and talked to him.
Yes.
He told me I was interested by faculty lecture. Oh. Now you can
All right, we're gonna roll up here. We're up next for our next dynamic duo.
yes.
Okay.
Yes. And the small
Good evening, one and all. The next session speaker is Ms. Catherine. It's my pleasure to welcome you back, ma'am. I would like to give a brief introduction about her career. She began her career in consulting working for Booz Allen and Ambleton and Radiant Crop. She developed Superfund policy in support of EPA in Washington, D.C. and conducted EHS audits globally for a variety of commercial and government clients. For the subsequent 23 years, she served in multiple leadership roles for General Electric in environmental health and safety and the industrial sector including aviation, locomotive and appliances manufacturing and services supporting employees and business operation. Glad to hand over the session to you, ma'am. Thank you.
Mrs. Lois has over 30 years of operation leadership experience in manufacturing, global sourcing, and project management. She has led multiple facilities in both unionized and non-unionized environments. She is an experienced sourcing leader in multiple industries, aviation, appliances, and industrial heating. Over to you, ma'am.
Thank you, everyone. So it's the Catherine and Lois show again. We're waiting.
I request everyone to come back and settle down. I request everyone to come back and settle down. Just another half an hour session is left. Kindly cooperate. Okay, you have only 2 minutes left with you to settle down. Kindly cooperate.
This next talk is on how to reduce greenhouse gas emissions, where they come from, what they are, and how we can impact them. So enjoy your break time. I think you had 2 minutes to come and rejoin and sit down, and Lois and I look forward to sharing this presentation with you.
I request everyone to come back and settle, please.
Ma'am.
Good afternoon. We are going to get rolling. Hope everyone has enjoyed their stand up and stretch time. And now we shall continue with reduction of emissions and specifically focused on greenhouse gases. So many people ask when you talk about air emissions, well, what's the impact of human emissions? Human-borne emissions versus nature, like a volcano. I mean, which one contributes more to greenhouse gas emissions? And so a lot of studies have been done in this area, and you will be interested to know that human contribution to greenhouse gases comes in around 90% versus natural causes, which may be a surprise to you, but that's the fact. And when we think about human-generated greenhouse gases, burning of fossil fuels is the largest human-driven source of greenhouse gases, responsible for over 75% of the carbon dioxide emissions globally. Okay, who came up with that? The Intergovernmental Panel on Climate Change. Okay, and on greenhouse gases, I should say that there are a lot of international groups, nonprofit NGOs, as well as for-profit companies studying and trying to implement reduction measures for greenhouse gases. Okay, so a lot of times we hear the term air emissions. You all may be studying this as part of your programs. And this generally, right, is a broader term than for greenhouse gases. So this is the very broad term, air emissions. It refers to the release of substances from various sources into the atmosphere, okay? And these can be natural emissions or man-made. And then greenhouse gases, on the other hand, specifically refer to the release of gases that trap heat in the Earth's atmosphere, contributing to the greenhouse gas effect. And when you think about these primary greenhouse gases, Lois is going to take us through the primary 4 greenhouse gases and what their impact is. And then as you, in your engineering and biology programs, think about your processes and you think about your businesses that your families run, you can think about where your sources of emissions are and how you might be able to reduce them. The primary greenhouse gases, I'll quickly summarize. Anybody know the number one greenhouse gas we always talk about? Anyone? Number one greenhouse gas. What is it? Carbon dioxide. Yes, sir. Nice job. And loud enough for me to hear. Perfect. Thank you so much. All right, Rampur, we're going to work on a little prize back here in a minute. Okay, hold for your prize. You can raise your hand. That's okay. We'll see you up there. Okay? Anyway, I appreciate you saying that. Yes, carbon dioxide is the measurement, the primary measurement for greenhouse gases, and many other gases are often converted into carbon equivalents, so there'll be one overall measure. Other gases that contribute to the greenhouse gas effect are methane, yes.
We are going to carry out your missions in the US after that.
And the memento is going to be all right. We need a mic perhaps over there for a name. Oh, does Rampur have a mic? If you would be willing to share your name and your program, can you hold your hand up again? Here you are.
Share your name and where you come from.
I'm V. Satish Subramani from Civil third year, and I'm basically from Bangalore and native is in Chennai. I'm from AMCEC Institute.
Thank you.
Civil third year.
Thank you. I appreciate your participation. Thank you. All right, I'm going to jump to understanding greenhouse gases. We talk about greenhouse gases, thank you, appreciate it. We talk about greenhouse gases a lot, but when you think about what they are and why that name came to pass, let's just have a quick recap, okay? Greenhouse gases, we see this acronym a lot, GHG, greenhouse gases. These are gases that are trapped. These four gases are often trapped. The atmospheric gases that trap heat from the sun and warm the Earth's surface. This is natural effect. It's called the greenhouse gas effect. However, this fact, while the effect is critical for life on Earth, this is an effect we need. Too much of a good thing is possible. And so, for normal, sustainable life on Earth, we need the greenhouse gas effect. However, human-initiated activities can increase these gases, intensifying the greenhouse gas effect and potentially leading to changing climate.
So why do we care about the greenhouse gases? If you take a look at the impacts are very extensive on the Earth, and you have the global warming and the climate change that are impacted by several areas, and then also the melting of ice caps and glaciers and our rising sea levels, which is going to impact a lot of our land that's around the seas. Also, the warming, and we heard Adrian talk about warming of waters and the impact on sea life. So the next one. So if we look at the major greenhouse gases, you know, carbon dioxide, that's burning your fossil fuels, and that emits the CO2 into the atmosphere, and that is the number one cause of our greenhouse gases. The number two cause is the methane, and you have a lot of your livestock farming, which is impacting that, also from landfills. And the methane is really effective at trapping heat in the atmosphere, which goes to melting the ice caps. On the number 3, we have the nitrous oxide, which is also, again, from agricultural activities, and then combustion of fossil fuels. And yeah, it has a very potent global warming potential. And then number 4 is fluorinated gases used in industrial applications and refrigeration. And so we like our air conditioning and making sure that we have air conditioning without fluorinated gases.
Thank you, Lois. When you think about sources of emissions, so now we know what the emissions are, and so in order to control emissions, we need to know what causes those emissions. What are the top sources? Energy production is number 1. Burning of coal, oil, and gas for electricity is the largest source of carbon dioxide emissions. And that's a fact. And that's why here at AMC, that's one of the things we really love seeing is the solar and some of the renewable energy, the wind, up even on the roof that we can see from this room. That's a wonderful way to, again, have a contribution to reduce your greenhouse gases. Transportation is another category. We're going to go into each one of these individually. Emissions, we talked transportation yesterday. Cars, trucks, ships, trains, planes, all generate greenhouse gas emissions from industry. Manufacturing, production processes emit a wide range of greenhouse gases, including carbon dioxide, methane, and nitrous oxide. Agriculture, the same, and waste management. There's some fantastic examples in waste management where methane gas is recovered from landfills. We'll get into a couple of those examples, and really we're seeing some better and better technology reuse scenarios in industry.
So if we look at the global and local impacts, I will talk a little bit about each of these. But I mean, health, agriculture, water, ecosystems, and then economic consequences. We come back to what is the cost and the impact from our economics. And looking at the agriculture productivity, all cost us money.
So I want to introduce a couple of important terms. So we've talked about what is GHG, greenhouse gases. In terms of business, what you'll hear, and this is important for those in this room, because what you'll hear is a couple of concepts that were developed by the Greenhouse Gas Protocol. The Greenhouse Gas Protocol is a partnership between the World Resource Institute and the World Business Council for Sustainable Development. Now, in order to have consistent terms, if we want to talk about reducing greenhouse gases, it's important to know what we're talking about so that across the globe, we can be focused on how we can reduce greenhouse gases. So one way is to have consistent terminology. And so what we've done is the Greenhouse Gas Protocol, this collaborative group, has defined the concept of scope 1, 2, and 3 emission sources. And so I'd like to talk a little bit about what those are, so you're familiar with those, and then ultimately you'll see that now when you look in a company's annual report. If any of you are also taking business classes, you're probably looking at annual reports for companies, and all of those now have a corporate social responsibility, or ESG section, environment, social, and governance section of their reports. And you'll see emission controls broken down by scope 1, scope 2, and scope 3. What? And so I'd like to quickly take you through what those definitions are. And if you'd like more information on the Greenhouse Gas Protocol and these scopes, on this slide, in the green, there is a link where you can get more information to learn more. So as you think about scope 1, scope 2, and scope 3, the quick slide is right here. You can take this slide, you can copy this graphic, you can pop it in your next presentation, And you can become someone who now can talk about what are scope 1, scope 2, scope 3 emissions. Scope 1, they're direct emissions from owned or controlled sources. So I have a boiler, I have it, and I generate my own energy from the roof, and I generate my own energy. Scope 2, indirect emissions are generated from the purchase of energy. So perhaps your renewables don't cover all the energy needs of the campus, so you also need to buy some energy. So that's an example of scope 2 emissions. Scope 3 emissions are everything else. Everything else in your supply chain or through your organization that generates emissions, and we'll talk a little bit more about what those are as we go on. This slide graphic does cover quite a few of those and gives you a sense of what happens. So scope 1. These are emissions from sources, as I said, that are under controlled by the organization, such as emissions from combustion and boilers, furnaces, vehicles, chemical production in owned and controlled process equipment. So managing scope 1 emissions often involves direct actions like improving fuel efficiency, switching to cleaner energy sources, or implementing energy savings technologies in operations. And what's interesting here, so there are a number of good examples in industry. I'm going to hold the examples till after I cover some of the basics on the definitions. Impact, reduction in scope 1 emissions can have an immediate measurable impact on an organization's carbon footprint. Replacing old equipment, I will just say, is one of the fastest ways to reduce your emissions and often reduce your energy bill. Old equipment is often uses much more energy. Sometimes people delay replacing equipment because it's a capital expense, but often what you'll find is as the energy expense becomes more expensive, your kilowatt hours become more expensive, you can look at your years of payback for a piece of equipment, and often that is coming down given the energy cost. Scope 2, indirect emissions. Your local utilities that generate energy, many are trying to incorporate more renewables. I'm from the state of Kentucky, and it's a big coal state. It's right next to West Virginia. There are a lot of coal mines in that part of the United States. And 90% plus of our energy in Kentucky, it's very inexpensive, but it's highly, it generates a lot of greenhouse gases because it's still predominantly from coal. So this is an example where in Kentucky there is a huge, huge effort by utilities to incorporate more renewable energy into the portfolio to ultimately bring down our emissions. And that's one of the most effective ways to do that, is work with your utility and with your local government, because sometimes those are very expensive investments by utility, and sometimes they'll work with local governments, even the federal government, for tax incentives to implement those programs. And so that's a great way to do a public-private partnership to implement those more expensive projects. Scope 3 emissions, as I mentioned, are all other emissions. Those in the supply chain that are generated from transportation. I mentioned yesterday during the transportation talk that one of the fastest ways to cut your emissions from transportation particularly is to look at, like in the US, I'll give you a real example. In GE Appliances, we switched our port of entry for most of our incoming goods from overseas, most of our supply parts. We used to accept them in the northwest part of the United States, up in the ports in Washington State. And then we trucked all of those items, some rail, but mostly trucked all of those items to the middle of the US, more to the east of the Mississippi River that cuts through the middle of the United States and north to south. So Kentucky, we were trucking all of these parts to Kentucky. We switched and started receiving the parts in Savannah, Georgia, and had a much shorter drive. And we cut our scope 3 emissions by almost 60% by switching ports, because trucking, the diesel trucks generate so much greenhouse gas emissions. And so we were able to measure that. We know how many trucks. The data is, for carbon accounting, is very precise. It's just like finance accounting. And so it's very precise, and you use emission factors to make sure you have the right thing. And I'm not going to teach you how to do that today, but it's the same as financial accounting. And that's why the SEC, the Securities and Exchange Commission for the U.S., is working on issuing. The new date is by April of this year, 2024. It was originally by December 2023. But the SEC, Securities and Exchange Commission, is issuing new reporting requirements for sustainability for corporate reports of publicly traded companies. So you will see more of that to come. And this carbon accounting will start to be reported just like financial data is what we expect in these reports. So again, important for business and important for design. Lois, I'll turn it over to you.
All right, so now that we've heard all of this bad news about how we're creating all this greenhouse gases, what can we do to combat it? So what we can do is take a look at energy efficiency and renewable energy. We can look at transportation. How are we transporting the goods, just like Catherine talked about? What are we doing from an agricultural and waste management? And then how are we helping the factories and the industry be more efficient? And so we'll go into each one of these. So number one, energy efficiency and renewable energy. So looking at all these different areas, homes and offices, industries, universities, what can we do to use more efficient renewable energy? And here are, these are basically your 4 areas of renewable energy. It's solar power, wind power, hydro, which is your water, and geothermal. And in my last company, we were very, very focused on reducing our scope 1 and scope 2 greenhouse gases across all our plants across the world. And we are building a expansion in the Utah facility, and that will all be used the energy for that facility will be from geothermal. And there's a university in Utah where they have about 90 buildings. About 75% of those buildings are using geothermal energy. And so Utah has really done a lot to really reduce those scope 1 and scope 2 energies. All right, and then the next one, taking a look at our transportation. So who has some sort of electric vehicle? Does anybody have any kind of electric vehicle? We got one. We got, okay, 2, 3, great. That's good. Sort of? It's a hybrid? Okay, all right. You know, the other thing we can do is carpool. You know, work with each other, and maybe one week you drive, the next week the other person drives. You know, do some things like that. And then, of course, public transportation. You know, and take and use advantage of those routes. I think, was I too fast? Yeah. I think this is yours.
Yes. And next we're going to have a look at agriculture. You know, this is, we have a lot of agriculture in the U.S. as you do here in India. So sustainable farming practices with crop rotation, agroforestry, integrated pest management, using organic fertilizers and reducing chemical pesticide use are all elements to help help with sustainable farming practices, reducing food waste, growing your own food, buying what you plan to eat. All of these lead to less spoilage, less in the landfill, less methane gas generation in the landfill, efficient waste management, promoting recycling and composting to reduce landfill use. Talked about that, encouraging reduction in single-use plastics and non-recyclable materials. Then you're producing less of those plastics. Not only are you disposing of less, but you don't need as many if you're using recyclable containers. implementing waste to energy systems where appropriate. There is a company called Waste Management, they're a global company, but one thing they've done in Kentucky, there's a large landfill there, and they reclaim all their methane gas, and they've designed a trash truck now, a collection truck, that only runs on methane. It's a very interesting, biofuel from methane. It's a very interesting concept. So they generate all of the fuel for this line of trucks that they have from their landfill. And they're really working hard to keep all that as one continuous cycle. As far as industrial opportunities, this is where we've spent the lion's share of our time in manufacturing, trying to reduce greenhouse gases. And again, technology upgrades and process improvements are the fastest way to achieve this. We replaced an old oven at GE Appliances that was a heat treat. And it took an inordinate amount of energy, and I think it reduced our total energy use at the site by 54% when we replaced it with a more efficient unit. So when you look at these things and you really do the calculation, there's the cost of the new unit, but you can't just look at that for your return on investment calculation. You must also look at what you save in energy over time to do the proper payback calculation. And that's simplifying that a bit, but it's important to look at your offsets. Emission control and monitoring. How do you know when a system is failing? If you're measuring and monitoring, you know when it needs service, when a filter needs to be changed out, when a control system needs to be serviced. Having continuous monitoring, sensors are getting so inexpensive and easy to attach and measure the right gases that there's almost no reason to have any output at a facility that you don't know what you're discharging at all times. The sensing devices are just getting better and better, so that's also something to look at.
All right, so what can we do? All right, and there's several areas that we can do. Here we go. So there's energy consumption, transportation, how are you getting your food, as Catherine talked about, consumer habits, like the EV vehicles and stuff like that. So how many people are doing things like this to help our environment? Now just think, I see 3 hands, and I know 4, 5, 6, okay, maybe one back there. So 7, let's just say 10 of you are doing these things. How much impact to the greenhouse gas do you think you're doing? Very little? Very little? So what if every single person in this room was at least doing one thing on here? Right? Then how much impact could we have? Maybe a little more? And then what if we inspired every single person in this university to do this? And then we started to inspire all of Bangalore to do this. We visited a facility that was a retirement home that was earlier this week. And they've done just this. They were very, very focused on creating an environment that was healthy for the animals, it was healthy for nature, it was healthy for them, and it was healthy for the earth. And it was a beautiful place. It had beautiful fresh air, and you could tell the difference when you walked into the facility. And so if you could just take that little microcosm and then spread that all to Bangalore, then you could start impacting India, right? So a lot of work to do.
Yeah, we met the architect that designed that facility, and I think when I retire, I might like to move there. It's very well done. It's really a fantastic facility. We talk a lot about where you can impact things from a corporate standpoint, from a governmental standpoint, but we didn't want to overlook what we can all do individually, which is why we included having everybody think personally about what we can do on a daily basis. This is a big topic, so I included it in the back of this presentation. After the question slide, when you get this, some very important links to very common terms that you will hear when people talk about greenhouse gas emissions and climate change. I'm just going to list out the terms, and if you're curious about these, this is where you can go for more information. The Global Reporting Initiative, Carbon Disclosure Project, Science-Based Targets Initiatives. These are all frameworks for setting goals around greenhouse gas reductions and other sustainability initiatives. The new Corporate Sustainability Reporting Directive that was just issued by the EU at the end of last year, and the new U.S. Securities and Exchange Commission Sustainability Reporting Requirements. As I said, the latest date, they'll be due out in April. And there's some excellent software that's out there and available today to do carbon accounting, and also have visibility through your supply chain on where and how you're generating carbon in your supply chain as a business or as an organization. So I just wanted to make you aware that these resources are here. And with that, we'll entertain any last questions.
Excuse me. Ma'am, have a question? This is quite important question, sir.
Okay. Are you a faculty or student? Oh, okay.
Not exactly a question, but I was curious on how GE is going to transition from, gasoline turbines to hydrogen electricity, hydrogen-based turbines or SAS. I was curious about that. Or is it going to be fully electrified? Yeah, I was curious on how GE is going to transition to a much sustainable form of, jet engines.
How is GE going to transition into a sustainable environment business?
Is it going to opt for electrification, or is it going to opt for SAS and hydrogen?
Is it going to opt for air purification?
Is how GE is going to transition to a sustainable environment. Yes. Question about GE.
So General Electric,
so I think I can answer that. So what we started to work on first, when we first started to set our goals, we said, what are we already doing well? What are we doing well today? And how can we measure that, quantify it, and then build on the things we're doing well? So for example, one of the things we were doing extremely well was we were on the journey to zero waste already. We were taking things, being very intentional about where and how we segregated and recycled plastics. As you know, if you segregate your plastics, you'll actually get paid to recycle them. If mixed-use plastics, it's very difficult. But if you segregate your plastics, then there's a much better opportunity to have those recycled. So we really tried to go after what we were already doing well. And then we started to work on the items where we knew it was also a business benefit. So what I mean by that is, I mentioned the transportation change that we made from port to port, moving our port. So that's a huge business change for us. We had to educate all of our suppliers. We had to, redo everything, and that, saved us, I think within the first 2 years, $9 or $10 million, or something like that on transportation costs. So that's a win, not only for greenhouse gases but also for the business. So I find where you can focus on strong return on investment and strong environmental impact are where you should focus first, and that's where GE continues to focus.
Thank you, Catherine. Okay, for asking a question, and probably unlike all the ones in the back bench, so we would like to recognize you with a small memento. Okay, and good luck to you. One more question.
Myself, Akshata from CSDS. Ma'am, my question is, there are mainly three greenhouse gases, carbon dioxide, methane and nitrous oxides. But why will we only stress on carbon net zero, carbon emission, ma'am?
Did you say, why do we center on the carbon emissions?
Yeah, ma'am.
It's the largest one, and I think initially some of those articles will give some additional, like a deep dive, everything you ever wanted to know about. Some of those will, on the GRI, and some of those other definitions will give you the long answer. The short answer is because the public was already familiar with the carbon, that making the others equivalent to carbon in their impact on the environment made it so it was easier for businesses to do the reporting, so it would be carbon and carbon equivalents, and it started to standardize the accounting. And so that's the reason, by converting to the same unit, just like you would have to convert to the same unit in any other math equation, it's kind of the same, where they've tried to standardize on one unit to make the math ultimately easier to do for carbon accounting.
Thank you, Catherine. Did you all get what you wanted? Good, wonderful. Only thing is, I don't have any, but remind me tomorrow. No, remind me tomorrow. Okay? Thank you. Thank you very much. Catherine and Lois, please come back.
Hello, ma'am. Ma'am, myself, Hafsa from Civil Department. I have a question for you. I belong to an agricultural village. Do you expect any greenhouse contribution? Greenhouse gases contribution? Agriculture.
Okay, yes. Catherine, emissions from the agriculture.
You said you belong to a group, and you're wondering what you all can do for greenhouse gas reductions? That's it. Okay, I'm almost there. Contributions from agriculture to greenhouse gases?
Yes, correct.
Yes. Yes. And I may need to just look up a couple things on that to give you the right level of detail, but nitrous oxide for sure from fertilizers is a huge area of contribution. So, and that's why that one slide talked a lot about sustainable farming, where you're using less fertilizers and fewer pesticides, which ultimately, back to Adrian's talk, gets in the water and then goes up to the sky, generates those algae plumes. So it's all, one big system, but that's probably the biggest contribution.
So you will give some information to her tomorrow?
Or today.
Okay.
Okay.
We will give you more information, and please remind me tomorrow. We will get you some recognition. Okay.
Thank you.
Thank you, Ms. Lewis and Catherine. Now the session has come to the last part. The last speaker is Ms. Robin K. Spencer. Robin K. Spencer is the environmental specialist for the West region of Sims Metal. She earned her certified hazardous materials manager in 1899. She is a trainer of record, qualified industrial storm water practitioner within the California Stormwater Association. She has been a member of the Society of Women Engineers since 1989. She was honored to be the member of the 2014 AHLP delegation to Bangalore and Goa. Welcome, ma'am. Welcome for the session. Thank you. This is the last talk. So, please, you can see that we have moved from information providing into more positive aspects. This last talk was great on greenhouse gases. Told us about the problems, but also offering solutions. So my talk is about resource recovery, which would be recycling, recovery, and reuse. There are a couple examples that I will give, but we'll just get through this, and there will be some class participation. Okay, first things first, what are resources? And we can bring mementos tomorrow for whoever answers. What would you call a resource? Did someone say water? Someone said water. Excellent. And Adrian had a good talk about that. Another, ores. Iron, minerals, zincs, metals. What else? Anything that comes from nature that humans have use for. Very good, thank you. So the field of resource recovery is very dynamic. There's a lot of engineering. There are a lot of very capable people working on it, a lot of entrepreneurs looking for ways to find better uses for waste. And at the same time, we're minimizing waste as we go through these processes. Okay, what materials are recyclable? Here we have the classic signatures for the different types of plastics. Some communities can recycle 1 and 2. Some can do 1 through 6. The problem is having the resources to process this type of plastic. We all like to recycle, and we try to, but sometimes there's not the ability to do so. So what materials are recoverable? We have a pile of scrap metal here. Up to 60% of the steel that's used in construction and producing toasters, cars, is recycled. It's a huge, huge industry. In the United States, California, where I live, I work with metals recyclers, and they fill up ships every month full of metal. Used to bring it to China, now it's Vietnam, India, Indonesia, where it's melted. Also on the East Coast, a lot of that metal is sent to Turkey, where it's melted and it comes back. We like to joke that it comes back as Toyotas and toasters, but just the basic metal recycling is an enormous example of recoverable product. What materials are reusable? Cardboard, fabrics, clothing,
When your clothing wears out, where does it go? If we can divert it from a landfill, it can be used as rags. It can be used for stuffing furniture. There's a lot of use. Some key trends and areas of focus in resource recovery include these items. We'll be talking more in sustainability about the circular economy. Again, it's kind of the cradle to grave. There are advanced recycling technologies, waste management, biological resource recovery, electronic waste recovery. There's a lot of initiatives. As I said, there's a lot of entrepreneurs who are doing amazing innovations to deal with recycling, reuse, and recovery. So collectively, these trends contribute to more sustainable and efficient approach to resource recovery and helps the environment. So some definitions here. Circular economy is designing products with recycling and reusability in mind. Take a car. There's a lot more aluminum in a car. Aluminum is one of the metals that is highly recyclable. We have minimized waste and maximized the lifespan of these materials. We have advancements in recycling technologies. Smart waste management allows for the data analytics to create more innovation and better resource recovery. Biological resource recovery. We're talking about biogas, which is methane. Livestock farming, landfills produce methane. E-waste. What do you do with your phones? Computers. You update them every few years. Where does it go? A lot of heavy metals, a lot of precious metals are in there. And the electronic waste recycler will recover those. Communities, governments, industries are working together through professional associations, trade associations, to look for commonalities where they can reduce waste. Part of our association, the Hazardous Materials Managers, does just that. We have so many people from so many industries who are working collaboratively. It's in forums like this that we're able to get a new idea or understand that someone's specialty could solve our problem. Again, material science. Are there any material science engineers here? No? Okay. But they're great. They develop, make use of innovative materials to replace less sustainable resources. And then educating consumers about responsible waste disposal. Do you want to just toss out our fabrics? Do you want to just toss out your plastics and your metal? No, it can be recycled. Governments play a big role in shaping resource recovery. That's why we have regulations. And one of the last ones is waste reduction. You remember the pyramid, we've seen it both in PPE and also waste. So first, you try to avoid the production of waste. You engineer it out. You reuse, recycle. You can use process technologies to minimize the waste or change it. At the very end, you'll have a landfill. Okay, a couple of examples here. Biological resource recovery refers to the process of extracting valuable resources from biological materials. One is methane. Think of the dairy farm. So what do cows produce besides milk? Other stuff. And that waste needs to be treated. So with a biogas treatment system, the waste can be mixed with some water. It's a slurry, goes into the biogas system. It will come out, the methane is separated, and that is an energy resource that can power communities as well as the dairy farm. Sheep also. I've heard in New Zealand, there's a couple pictures from New Zealand, that there are maybe 3 or 4 million people and 3 times as many sheep. So they have a significant methane production capability. And there are some big issues on, and then clever ideas about how to capture that methane. Other places, you can use your food scraps, agriculture residue, sewage sludge, and can be processed in anaerobic digesters, where the microorganisms break down the organic matter and produces that biogas. Here's some examples in Japan. They have these biogas treatment plants. Okay, metals recycling. Does anyone recognize this car? Yeah. This was the first car manufactured in India. It's really cute, but I'm sure it's not on the road anymore. So what do you do with it? What's in a car? A lot of steel. A little louder. What else is in a car? Fabric, upholstery, rubber, plastic, glass, aluminum, oils, gasoline, brakes. A lot of things are waste. So when you go to recover a car, you want to drain the fluids. The gas can be reused, reprocessed. The oil can be reused, reprocessed, filtered. Even the mercury switches that were in older cars, that mercury can be recovered and reused. Okay. So what do we have in a car? Steel and iron. Okay, I said 60%, but this is later data. 88% of steel used today is recycled and reused. That's really great. Big, big industry. There's a lot of aluminum, there's copper, lead batteries, there's platinum, palladium, rhodium, precious metals that are in the catalytic converters. Where I come from, the cars with catalytic converters are big targets for thieves. Catalytic converter will bring in maybe $800, maybe $1,000 by a thief. And they're so experienced, they can just saw it off in the middle of the night and people are left. These are Toyota Prius, the hybrids. Gold and silver, magnesium. All of these are metals that are reused. So the shredding, how do you get it? You have a shredder. Metals are separated, processed, and then sent to smelters to recover the steel. And then what about the other stuff? The copper, how do you get it? The brass. Stainless steel. And there's mechanical and manual techniques. So first of all, you have a car that goes into a great big shredder, and appliances, white appliances, tables, chairs, refrigerators. But first you'd want to take out the Freon and any other refrigerant, and oil is in that. So it breaks the car down into smaller fragments. The reason you want to take the oil out is because it will contaminate the product that you're trying to recover. So you want as clean a source as possible. There's magnetic separation. So steel will come out, iron. There's an eddy current separator where your non-ferrous metals, copper, aluminum, is spun out by electrical means. Error classification, lighter ones. There's even floating vats which will separate different metals. Manual sorting, sometimes it's necessary to have pickers on a line that will separate the small pieces of copper, which is very valuable, from lighter weight materials. Density separation, again, this would be the liquid separation. Sometimes chemical processes are used. Okay, what do you have? Well, what happens after you separated the metals? What's left over? Again, the plastics, rubber, glass. So treated or shredded waste can be used for alternative daily cover in landfills. One of the shredder plants in the San Francisco Bay Area produces about 30 very large truckloads of this treated shredder waste every day. In California, shredder waste is a hazardous waste unless it is treated. And we treat it with concrete, fly ash, a silicate to bind the metals and anything else in it so it doesn't leach out at the landfill. So we solve a lot of problems. Landfill gets this alternative daily cover because they're putting down lifts of garbage and they cover it every night. And then the next day, there's that day's garbage and they cover it every night and roll it out. Okay. Do you have any thoughts on resource recovery here in India? What are some innovative technologies that are being used that you're aware of or that you've learned in some of your classes? And we have one more item, don't we, Kendra? One more memento to give out. Okay, but still. Yeah, we'll give it to you tomorrow. Does anyone want to comment on India's process or Karnataka's? Yes, please.
So thank you so much for the wonderful talk. Now, what happens in India is that there is a lot of leaf which falls on the roads. Leaves, the tree leaves, right? So I think that's a huge resource in some way or the other, right? Because I think the leaves can be used in certain different ways. I'm not sure, but we all waste that leaves in some way or the other. So are there any ideas that you can give so that we can use those as a proper resource in a resourceful way?
So the comment was there are a lot of leaves on the streets. What happens to those? And do your sanitary workers pick them up?
Yeah,
do they throw away?
In a very stratified way. Some people, in some cities it is taken well care of, in some places it just gets wasted, it just goes down.
Well, the best thing to do with leaves is to create mulch, compost. You know, if there is some manner of collecting them and putting them in a pile, mix them up with food scraps, then they become organic material and can be used, you know, as mulch. What we do in California is just that. We actually have a bin where yard waste can be put. So when the leaves are falling, somebody has some grass they've mown, cut trees, we can put it into the green bin. That is taken to a section of the landfill and all dumped. Food scraps from restaurants go there, all mixed up, heats up, and then consumers, the population can come and get free mulch for their gardens. So that's how we do it in our community. And biogas. That's right. I mean, you're making methane. Yes, thank you for that comment. All right, is it one more?
Hello, it's a really nice discussion you've been holding on today. So I'm coming from an e-waste recycling company, right? So we're trying to recycle e-waste and we're working on urban mining. We're working on urban mining where we recover precious golds and metals from phone recycling. We're technically focusing on computers, personal computers recycling. Right, so we're also very much into the view that when you're reducing greenhouse gas emissions, like Catherine just pointed out, you're using lithium-ion batteries into EV vehicles, right? We're using lithium-ion batteries into electric vehicles. So when you're using lithium-ion batteries into electric vehicles, to manufacture that very lithium-ion battery, you're using a lot of energy per se to manufacture it. Suppose you're using Tesla batteries per se, it uses 2,400 to 1,600 kgs of energy just to manufacture it. So that's producing a lot of greenhouse gases by itself. So at the end of the day, how are you actually reducing emissions? By the very recycling process or by using an alternative mechanism like lithium-ion batteries or metals recovery? What is the end mechanism or alternative to all of this? How does it work?
It's a long question. But
I'm going to give a short answer. This is something that my son asked me. And about lithium batteries, it is difficult to recover. The energy required to produce them is great. So what are the trade-offs? I don't have that answer. You know, just like you. You know, on one hand, we have the noble thought of using electricity, but on the other hand, we are using all these resources. And what is the energy cost for them? It's a big question. But thank you for your comments.
Robin, if you permit me, I will add a few things. If you permit me, I will add a couple of items to what you said. Is that okay?
Please.
Okay. The estimations are a research type activity. There are people who are working on that. We have to look at their publications to get more details about it. It's a tremendously important question because we all jump into battery system all the time and say, this is a super solution. Okay.
So we are able to get recovery and recycling. So we are into recycling as well, electronic waste. So we don't have a trade-off per se, so we thought you'd have better suggestions. So she's an expert.
Good. Now, I don't have any mementos. Hold for a second. Hold on. I don't have any mementos now, but we do like to recognize you tomorrow with one of the mementos from our team. So in the meantime, our professor said we give a, give me, I have to use my right hand. Okay. So, thank you very much.
And
Thank you,
for
Robin.
Thank you, Rampur. Thank you for your participation. Safe travels home, and we'll see you tomorrow. One more thing? Okay. Bye-bye.
Thank you, Robin Spencer, for giving a valuable session. Thank you all the audience for your patience for today's session. I request everyone to be present tomorrow at 9:30 session for the session. Attendance is mandatory, and thank you once again for making today's event successful.